The Earth's weather systems are driven by complex interactions between temperature, pressure, and the planet's physical features. At the equator, the sun's energy is concentrated, while at the poles, the same amount of energy is spread over a larger area, creating temperature differences. Imagine a pocket of air at the equator surface. As the sun heats this air, the molecules move faster, causing it to expand. The same amount of air now occupies a larger space, which decreases its density and causes it to rise due to buoyancy. This creates a lower pressure area at the surface as fewer air molecules remain, and a higher pressure region above it as the rising air accumulates. Nature tends to move towards equilibrium, so air from high pressure areas flow to fill lower pressure zones, creating what we know to be wind. The rising air at the equator moves poleward at high altitudes, eventually sinking at the poles, where cold, dense air creates a high pressure region. This air then moves back towards the equator's low pressure zone, effectively circulating the atmosphere. Now, this is a bit of a simplification. The Coriolis force caused by Earth's rotation actually breaks this circulation into 3 atmospheric cells, which are responsible for shaping the prevailing winds. It's important to note that because land heats and cools quicker than water, it creates sea and land breezes in a manner similar to atmospheric circulation, but on a much smaller scale. Moisture enters the atmosphere through transpiration and evaporation. As warm air rises and cools, it condenses, forming clouds. This happens because cooler air can hold less water vapor than warm air, which is also why dew forms overnight when surface air cools. When water droplets in a cloud grow large enough, they fall as precipitation: rain, snow, sleet, or hail, depending on the conditions through which they fall. When ice crystals and soft hail collide in a thunderstorm, the heavier hail becomes negatively charged and sinks, while the lighter ice crystals become positively charged and rise with updrafts. This charge separation creates a strong electric field that, when the air can no longer insulate against it, discharges an electric current. The extreme heat from the lightning rapidly expands and compresses the surrounding air, generating a shock wave, which we hear as thunder. Thank you for watching. You can find all of this in more detail for free at